This video is to give an explanation and background on finding the area under a curve using certain endpoints. We'll start with 6 left endpoints, but notationally we're looking for the area of the function 12 over x from 1 to 4. Now, as you can see, graphing it gives us a great visualization of what area we're even trying to find. So I already broke up my picture into 6 rectangles here. Now to find those rectangles, since I'm using left endpoints, I'm going to start with that left bound of 1, and I'm going to go all the way up to the function, put a dot there, and then I just make my rectangle based on how big my widths are for each of these rectangles. To find that, since I knew it was from 1 to 4, I can subtract these two, which would be 3, and just that distance split it up into how many pieces. Now we might ask you to do 6, 8, 10, however many pieces or rectangles, and you just divide it by how many bars we're going to have there. So in this case, each width is going to be a 0.5 distance. Now again, the goal of this is to find the area under this curve, which estimating wise would be the area of these rectangles. So we want to look at the area of these rectangles individually, how we get those heights, and then how we can actually use the summation for that. To show this, I'm going to move my rectangles from my graph to the side here, knowing that my width is 0.5, but thinking about how I find that height. If I look back at my graph, it's as if I'm plugging 1 into the function. So in this case, this would be 12 over 1, which would be 12, for a total area of 6. I'm going to add the others and move them over. So as you can see, you can do this by hand. You can find each area by knowing that the base is 0.5, and then the height comes from the computations above. So I tried to show that up here, that 12 divided by 1, 12 divided by 1.5, 12 divided by 2, so on and so forth, and then just taking my base times my height. To find the total area, I'd add each of these up to get a total of, looks like 19.114, that 12 sevenths. Isn't the nicest, but a lot of these were for our first example. Now that's all great to be able to do it by hand to kind of see where this is going, but we do have an addition down here. We have a series, or want to make it into a series, and we'll see if we can use what we learned from sigma notation. But we notice that we have this constant 0.5, and that the shape or the size of the rectangles keeps changing. So somehow I'm going to have to find these areas based on my inputs of like 1, 1.5, 2, 2.5, so on and so forth. So I move my rectangles back to think about what I'm actually inputting, what's actually changing in this problem. So I know that the area of rectangle is always based on type, but since I have equal spacing in my bases, I'm just going to take the base, 0.5, times the height. But the height is a function and it's changing with x. So really what I have to think about is how is x changing? You can see the pattern of the inputs below here, that normally I would plug in x to find the output, but now it changes from 1 to 1.5 and 2. So what we're going to do is make a left bound pattern. The left bound pattern is just saying what values of x are you plugging in. So first I have 1, then 1.5, then 2, then 2.5, all the way, I'll just write them all out, it's not too many, 3, and then it stops at 3.5. So let's see if I can actually make a pattern with this. Well, this looks like an arithmetic sequence. So let's see if we can write an arithmetic equation for that. So just noticing that we have a jump step or a slope, a common difference of 0.5 each step. So I just 0.5x and then plus 1. Now again, why a lot of times we've talked about that in CP/M they wanted you to go back a step, but in this case we're going to tie this to sigma, so we want to make sure that I can plug in 0 first and get that initial output, which sounds funny because this initial output will become my first input. So let's see how this ties with sigma. With my sigma, really I have to build something that will add all the areas. So let's go back and think about that area again. The area is the base times the height. But we said the height is what's changing. The base is actually constant. So really for each term in this, it's going to be 0.5 times something. But let's think about that height. The height we're actually finding from the function. So I would take 0.5x times whatever 12 over x is. But let's step back and think about what would happen in the sequence, or the series here. Now, let's say I started at x as 1, for example, because I wanted to plug in 1 first. Well, if I do that, I'm going to plug in 1, and it would actually give me the correct first area. But then it's going to say x is going to 2. Well, but that's only going over to the red, and then it would go to the orange. So somehow I have to manipulate what my input is. I manipulate the input because I want it to plug in 1, and then I'm going to force it to plug in 1.5, and I'm going to force it to plug in 2, and then 2.5. So think about how we can do that. And that's where the pattern of the left bounds comes into play. If I put the pattern of the left bound, instead of dividing by x, I'm going to manipulate really what it's going to plug in, quote unquote, that I'm going to plug in 0.5x plus 1 into the denominator. Now I go to my indices here that I want to see what would I plug in for x to get a 1 first, and then I do want it to divide by 1.5, and then I want it to divide by 2. So if I put in an x as 1, that's not great because then it'll put in 1.5. I want it to just divide by 1, so I'm going to start x at 0. Now let's see if it's finding me the correct heights. If I plug in 0, it would be 12 divided by 1 times 0.5, there's my 6. Now if x is 1, look what happens. It's going to do 12 divided by 1.5 times a 0.1. That's my green. Then it's going to plug in x is 2, good to go, because 1 plus 1 is 2. And then it'll plug in 3, but that'll be this 2.4, and then so on and so forth. So actually, this gets me each of those inputs correctly. But like we've been working in class, where does it stop? So in this case, I have to think about what's the last value I'm going to plug in, and that is this 3.5 if we're talking left bounds. So I think, okay, what would I plug in here to get a 3.5 on the bottom? And that goes up to 5. At this point, this is your series that will find or add up all of the values for that. Let's try it in our calculator. To recap the calculator steps, I'm going to go math. It's option 0 down here, so you could just press 0 right away, and we'll get our summation. Let's put our x starting at 0. Top input will be 5. A lot of parentheses for this. So I'm going to go 0.5. You could put that in parentheses, but I'm going to start another parenthesis. I'm going to go 12 divided by. Now, anytime we have some sort of linear multiple term thing in a rational here, put an extra set of parentheses. 0.5x plus 1. Close that parenthesis, and we'll get here 19.114 that we got before, which feels great. But what we usually talk about next is this an overestimate or an underestimate? And as you can see, when we have the left bound, or left endpoints, I should say, for these rectangles, you can see a lot of the area above the curve. Now it depends if this function is decreasing or increasing, if it's going to be overestimate or underestimate, if we're using left compared to right. So it's a lot of times visualizing it. So since this is an overestimate, maybe let's see what it would look like if we had right bound rectangles. Maybe worthwhile to show you how I'm getting these right bound rectangles is now I'm going to start right to left. But I'm actually going to start on 4, go up to the function value, and then I'm going to make my rectangle. Go to 3.5, up to here, straight across, and then straight down. Let's go red, straight up, hit this value, straight across, then down. I'll keep going with that pattern. And as you can see, this is underestimate, but we'd still want to be able to find the area under the curve. And I'm wondering if I can use my summation to help me. Now, again, what really changed is the heights that I have. This is still 0.5. Now, a lot of these heights are still using the function 12 over x, but it's really what the input is that's telling me the height. For example, in the black rectangle here, the height is using an x value of 1.5 to start off with. And then I wanted to plug in 2 and then 3, or sorry, 2.5. Then I wanted to plug in 3 and 3.5, and I do want it to plug in 4 this time. So instead of making a left endpoint pattern, let's make a right endpoint pattern. Now I have a right endpoint pattern, and I can plug this 0.5x plus 1.5 in right here. So that x is 0. That's one way to do it. But I think I have an easier way for you. I mean, really, this 0.5x plus 1, those values are in here. It's just a matter of what I'm plugging in and where I stop. So I can still put in 0.5x plus 1, but I got to think about what x is, or my first input for x, to get now a 1.5, and then a 2 and 2.5, and then I want it to stop at 4. Well, really, if you look here, if x is 1, don't I get 1.5? And then if x is 2, I get my 2, 3, 2.5, 3, 4. Oh, but now instead of my last value being 5 to plug in, I need it to spit out 4. So really, if I plug in 6 here, that'll find me some of the right end patterns. So if you're able to build the argument for a left end, you can actually use the same argument and just kind of shift which values you're using as your inputs to use the right endpoints. 0 goes to 1, 5 goes to 6. Let's try it out in our calculator. Nice little calculator trick is if you just press second enter, it'll bring back your last keystroke. May not be the most efficient, I do have to go back, but I'm only changing 2 things. I'm just changing this to a 1 and to a 6. So this will be 1 now. This changes to a 6, and I press enter. There is the right bound. As you can see, overestimate, underestimate. And the true region, or the true area under there, is somewhere in between that. We're at pre-calc level. We're just trying to visualize where it is. What you may want to think about is how can we be more accurate? At this point, we're going to say, you know what, use 6 endpoints. What would happen if I did 8? What would happen if I did 10? And think about what does that change in my sigma here? Does that really change my argument? Or does it just change the indices and my pattern from there? So hopefully this helps, and we'll get more practice with that in class.